This section deals with logarithmic functions, and in this particular section we're going to be changing from logarithmic to exponential form, and from exponential form to logarithmic form. We'll be evaluating logarithms. We'll be using the basic logarithmic properties, also use common logarithms and natural logarithms. We'll first define what a logarithmic function is. For x is greater than 0 and b greater than 0, with b not equaling to 1, y is equal to log to the base b of x is going to be equivalent to this particular expression or equation. B to the y equals x. Okay? And the function log to the base b, f of x equals log to the base b of x, is the logarithmic function with base b. So here, y equals log to the base b of x will be equivalent to b to the y equals to x. And in this case here, you want to know the location of the base and the exponents when you're dealing with exponential and logarithmic forms. Of course, logarithmic form is y is equal to log to the base b of x. Here, this b, that's the subscript for the log, that's your base. This y represents the exponent. So when you're finding the log to whatever the base is of some number, you're just basically finding out what the exponent is. And then exponential form is this: b to the y is equal to x. Here, this b is going to be your base, and the y is going to be the exponent. Okay. And here's a study tip that will help you convert from logarithmic form to an equivalent exponential form. Here we got y is equal to log to the base b of x. That means this. This b is your subscript, that's your base. That's going to be to the exponent, which is y, equals to x. So this is a study tip that I encourage most of my students to use to help them convert a equation that's in logarithmic form to an equivalent exponential form. And we'll use that to do these type of problems. Like in part A, B, and C, you're going to write each equation in its equivalent exponential form. In part A, you got 3 is equal to log to the base 7 of x. Okay, so here we're going to convert that into its equivalent exponential form. So the subscript for the log is your base, which is 7. That 7 will be the base for this 3, which will be your exponent for 7. So you're going to have 7 to the third, then that's going to be equal to what's immediately after the log will be x. Okay, so this will be 7 to the third equals to x. That will be your answer in its equivalent exponential form. Okay. Now part B, we got 2 equals log to the base b of 25. 2 equals log to the base b of 25. And we're going to write that in its equivalent exponential form. All right, in this case here, the subscript for the log is b. That b will contain the 2, which will be your exponent. So this would be b to the power of 2, or b squared, equal to whatever is after the log. That's 25. Okay? Because this right here is always the base, the number or the expression after the equal sign or in front of the equal sign. That's going to be your exponent for that base. Okay? So it's b to the second equal to 25. That's the equation in its equivalent exponential form. And finally, part C, we got log to the base 4 of 26 equals to y. Log to the base 4 of 26 is equal to y. Now, it's written a little bit different from parts A and B, but still it's done the same way. Here the base is 4. That's your base right here. That's the subscript for the log. That y is going to be your exponent for 4. So it'll be 4 to the power of y, and that's going to be equal to 26. Okay, so that's how you'll convert a logarithmic equation into an equation in its equivalent exponential form. Okay. All right, now let's go the other way around. And in this case, we're going to have equations in exponential form, and you want to convert that into its equivalent logarithmic form. So in part A, you got, let's see, 2 to the 5th equals to x. 2 to the 5th power is equal to x. And you want to convert that into its equivalent logarithmic form. So here, in this case, the form will be this. We always have a log. The subscript is always the base of, now I'll just say the answer, which is usually after the equal sign when it's in exponential form. And it's always equal to the exponent. That's usually the basic form for that. You always have a log in it because you're converting it to logarithmic form. The base will be your subscript, and whatever is after that equal sign in exponential form will be the answer, which is going to be next to the log, and then the exponent will be after the equal sign. So when we write 2 to the 5th equal to x in logarithmic form, it will be log this 2, which is the base, that'll be the subscript for the base. That 5, which is your exponent for 2, will go after the equal sign. So the x will have to go after the log. So in this case here, it'll be log to the base 2 of x equals to 5. Okay, part B looks like this. B to the 3rd is equal to 27. And we want to write that in its equivalent logarithmic form. Okay, if we're going to write something in logarithmic form, we always have log in it for the log. The b is your base, so that will be the subscript for the log. We know the exponent for 3 for b is 3, so that 3 will go after the equal sign. Because when you're taking a log of something, you're always finding out what that exponent is. So here the 27 will have to be immediately after the log. So it'll be log to the base b of 27 equals to 3. And then finally part C, e to the y is equal to 33. E to the power of y is equal to 33. In this case here, we write log for the log. The base here is e. That's going to be the subscript for the log. Now, the y, that's your exponent for e. That goes after the equal sign, because the log of something is always going to be equal to the exponent. Then this 33 goes immediately after the log. So in this case here, this will be log to the base e of 33 equals to y. Okay, so that's how you'll convert an equation that's in exponential form to its equivalent logarithmic form. Okay. All right, next we're going to be evaluating the logarithms. And some of these can, well, most of these can be done without the use of a calculator. Okay. Like in part A, you got log to the base 10 of 100. Because you're basically trying to find out the exponent. So here we got log to the base 10 of 100. Okay, and this is going to be equal to, and I'll put a box here, because we're trying to find out the exponent for 10, such that 10 to what power would give us an answer of 100. So we want to find out 10 to what power would give us an answer of 100. And in this case, it will have to be 2, because 10 to the second is 10 times 10. That's going to give us 100. So that means that log to the base 10 of 100 is going to be 2. And that will be our answer, because we're just basically finding out the exponent when we evaluate logarithms. All right, part B looks like this. You got log to the base 5 of 1 over 125. Log to the base 5 of 1 over 125. Okay, so here we're basically trying to find out 5 to what power will give us 1 over 125. Okay, now I know 125 is a power of 5, because if I break 125 up into an exponent, well, a power of 5, it will be 5 times 5 times 5, or 5 to the third. So I'll rewrite this as 1 over 5 to the third. And I have to use the concept of negative exponents. If I have a positive exponent in the denominator, when I rewrite it, it'll be negative. So it'll be 5 to the negative 3. And obviously that missing exponent here will have to be negative 3. So log to the base 5 of 1 over 125 would equal negative 3. All right, part C. Log to the base 6 of 36. Okay. I need to make a correction here. This is log to the base 36 of 6. Okay. Okay. Log to the base 36 of 6. The 36 is your base. And the exponent you're trying to find for 36. So 36 raised to what power would give us 6? Okay. Well, I know if 6 to the second power would give me 36, then the reciprocal of 2, which is the exponent, which would be the exponent for 6, its reciprocal would be 1/2. So that means that 36 to the 1/2, which is like the square root of 36, would give me 6. So that missing exponent here would be 1/2. I'll repeat that again. Here, if 6 to the second is 36, then that means for me to go from 36 to 6, and 6 to the second is 36, the reciprocal for 2, which is the exponent, which would be the exponent for 6, would be 1/2. Take the reciprocal here. So I had to kind of work backwards to get this particular exponent here. I'm going from a large number down to a small number. And I know 6 squared would be 36, so 36 to the 1/2 would be 36. And part D, log to the base 3 of 7 to the third power. Log to the base 3 of 7 to the third power. So we're trying to find out 3 to what power would give us the 7th root of 3. Now what I'm going to do here is rewrite the 7th root of 3 in its equivalent exponential form. Okay, so this will be a 3. This exponent for the 3 is 1. That's your numerator. the index is 7, that's going to be the denominator. Okay, so here the missing exponent obviously would be 1/7. So log to the base 3 of 7 of the 7th root of 3 would be 1/7. Okay, so that's pretty much how you will convert evaluate logarithms. You're basically finding out the missing exponent in each of those problems. All right, let's look at some basic logarithmic properties. 2 of them involve the number 1. Like in this case here, log to the base b of b is equal to 1, because of the fact that b to the first power would give you b. Okay, and then log to the base b of 1 is equal to 0, because of the fact that b to the power of 0 would give you 1. Okay, so those two involved the number 1, like these two right here. Log to the base 9 of 9. You're basically finding out 9 to what power would give you an answer of 9. And that's obviously going to be 1. And then part B, log to the base 8 of 1. Well, 8 to what power would give you 1? It's only one number for that. That would be 0. So here I'm just applying these two properties that involve 1 with these particular two examples. Okay. All right, the next one involved inverse properties. These two involve inverse properties of logarithms. Here, if you have b greater than 0, where b is not equal to 1, log to the base b of b to the x is just simply going to be x. You can think of it as this base for the subscript for the log, and this base b, they're the same. We can cancel those out. Those are inverses of each other. That's going to give you x. And also, b to the log to the base b of x is also x. So b and log to the base b are inverses. They can cancel. You're left with just simply x. So here you apply. We can apply these two inverse properties to these types of problems. Like in part A, we want to evaluate log to the base 7 of 7 to the 8th. Okay, log to the base 7 of 7, that's gone. It'll just be this exponent, which is just simply 8. That's all there is to it. Part B, 3 log to the base b, 3 log to the base 3 of 17. 3 and log to the base 3 are inverses. We can negate those. We'll be left with this number right here, 17. Okay. So that's how we use inverse properties of logarithms to evaluate these types of expressions. Okay, let's look at the domain of a logarithmic function. The domain of a logarithmic function is always going to be the set of all positive numbers. That means the domain has to be where x is bigger than 0, meaning that x can't be 0 and x cannot be negative. It must be all positive numbers, because we can never take the log of 0, and we can never take the log of a negative number. Those are undefined. Okay. Next we'll look at is common logarithms. A common logarithmic function is the logarithmic function with base 10. In other words, f of x is equal to log to the base 10 of x is usually written as just simply f of x is equal to the log of x. So if you do not see a subscript for the log, is understood to be 10. This is a common logarithm, meaning that the base is understood to be 10. And we do have a log key, or the log key, on our calculator that we can use to evaluate common logarithms. Okay, it's the sixth key on the far left-hand side of your calculator if you have the TI-83 or 84 plus calculator. All right, let's look at this particular example where it says here that the percentage of height attained by a boy who is X years old can be modeled by f of x is equal to 29 plus 48.8 times the log of the quantity x plus 1, where x represents the boy's age and f of x represents the percentage of his adult height. Approximately what percentage of his adult height has a boy attained at age 10? Okay, so here's the function, and here x is going to be equal to 10. So we're going to be evaluating f of 10. And we just simply replace the x in our f of x function with 10. So we're going to have 29 plus 48.8 times the log of 10 plus 1. Now this we can just type into the calculator as is. So to do that, all we do here is just type in 29 plus 48.8. Now there is a log key, which is right here. We'll press that button for log, and then we can type in 10 plus 11. 10 plus 1, I'm sorry. 10 plus 1, and then close the parentheses. And then from that, we can go ahead and press enter. And we get, in this case, 79.81996304. Now, they say to the nearest, let's say to the nearest whole number, to the nearest whole percent, which will be 80%. So this will be approximately 80%. So by the age of 10 years old, this boy would have attained 80% of his adult height. Okay, so that's how we apply logarithms to this particular problem here, and how we use the calculator to evaluate logarithms. Okay, and here's some properties of general logarithms. Common logarithms. These are similar to the properties of general logarithms that I discussed earlier. In this case, a log of 1 is going to be 0. The common logarithm of 1 is going to be 0. The common logarithm of 10 is 1. These two involve the number 1. These two are inverse properties, where log of 10 to the x is x, which is that exponent. And then this one, 10 to the log of x, is going to be x. So pretty much 10 and log to the base 10, those are inverses. You can say cancel, which will be x. Okay? So these are just pretty much a precursor of the general properties of common logarithms. You can see they're pretty much the same, but here we're just using common logarithms in this case. Another example of common logarithms would be to use the formula r is equal to log to the base, log of I divided by I sub 0. That's r is equal to log of I divided by I sub 0 to solve this problem. If an earthquake is 10,000 times as intense as a zero-level quake, that's I is equal to 10,000 I sub 0, what is the magnitude on the Richter scale? So here, we're dealing with this formula, And we know that I is 10,000 I sub 0. That was given to us in that particular problem. And we want to find out what that magnitude is, which is R. And that's going to be log of I, which is in this case 10,000 I sub 0, divided by I sub 0. Okay, now the I sub 0's divide out. You're left with R is equal to the log of 10,000. Now what I'm going to do here is rewrite 10,000 as a power of 10. As you can see, in 10,000 there are 4 zeros, so 10,000 will be 10 to the 4th. So I have R is equal to the log of 10 to the 4th. Then I can use one of the properties of logarithms. The log of 10 to whatever that exponent is that exponent. So log of 10 to the 4th will simply be 4. So the magnitude here would be 4. Now again, you can type in by pressing the log key and then 10,000 and then hit enter. You'll see that the answer would be 4. Okay, but I was just showing you how you can use the properties or the common logarithm properties to do this without the use of a calculator. Okay. All right, the next thing we'll look at is natural logarithms. Okay, the logarithmic function with base e is called the natural logarithmic function. If you have base e, then that means we're going to be dealing with a natural logarithmic function, meaning this. F of x is equal to log to the base e of x. It's just simply going to be f of x equals ln of x, meaning the natural logarithm of x. And we read that as ln of x. And the calculator that has the ln key, which is the 7th key on the left-hand side of your calculator, we can use that to evaluate natural logarithms. And the domain, again, just like the logarithmic function, its domain is all x values such that x is greater than 0. We can't take the natural log of a negative number. We cannot take the natural log of 0. Those are undefined. And these are the properties of natural logarithms. Just like we have properties of common logarithms and the general properties of logarithms. Ln of 1 is 0, and ln of e is 1. These two involve the number 1. These last two are inverse properties. Ln of e to the exponent x is that exponent, x. And then e to the ln of whatever the expression is that expression. E to the ln of x is x. So those are inverse properties. Ln and e are inverses of each other. Okay, now let's look at an application of just those natural logarithmic properties. Like in checkpoint number 11. Well, in this particular problem, we have the function f of x is equal to 13.4 times the ln of x minus 11.6. This function models the temperature increase, which is f of x in degrees Fahrenheit after x minutes. Use the function to find the temperature increase to the nearest degree after 30 minutes. Okay, so here we know x is 30, and this is our function that we're going to be using. So we'll basically just evaluate f of 30 by replacing the x with 30. So it'll be 13.4 ln of 30, and then minus 11.6. Now notice I put the 30 in the parentheses because I'm only going to be taking the ln of 30. Okay, so on the calculator, you're going to be doing this. you're going to type in 13.4 and then press the LN button, which is right here, LN, and then 30. Now make sure you close the parentheses around the 30, because if you don't, you're going to get a wrong answer, because you only want the natural logarithm of 30, and it's going to be multiplied by 13.4. And whatever that is, we're going to subtract from it 11.6. So your screen should look like this: 13.4, then ln of 30, close the parentheses around the 30, minus 11.6, and then press enter. So here, I'm not sure how they want this. To the nearest degree will be 34. Here, 33.9, we round it off to 34. So f of 30 is approximately 34 degrees. So to answer that particular problem's question, we want to find out, well, the temperature increase after 30 minutes will be 34 degrees. Okay, so this is how we use the ln function to evaluate the natural logarithms of anything. And keep in mind that the value of x can't be 0 and x can't be negative. So that will conclude this section on logarithmic functions.